G'day, you're watching the Aussie BIM Guru. Today I'm going to go through the second part of a three-part series that I'm running on Solar Responsive Facades. So you might have seen my last tutorial where I covered Dynamo and imagery. So basically how to pixelate and manage image files using Dynamo for Autodesk Revit. But the second part I'm going to cover today moves on from image management and deals with conceptual massing and adaptive components, and I'll run through these from the basics up to the final product for those that haven't built them before. So we're going to look at curtain panels by a surface pattern. So we're going to use a case study, which is the Kiefer Technik Showroom by Ernst Giselbrecht, and you can see the panels are kinetic. So basically they can move as the sun moves during the day. The facade will adjust to accommodate the optimal shading layout based on not only the building's internal programming, but also the solar exposure on the facade. So essentially the panels will pivot to expose more of the facade. So we're going to look at replicating that in Revit using a technique called adaptive components, which is quite handy for complex and conceptual massing. And we're going to use a tool literally called Conceptual Massing as a framework for these panels to bring into our model, ultimately so we can apply this facade in our BIM model as a design system. But without further ado, we'll move on to the demonstration. So we're going to use a curtain panel by pattern. Now you might have seen curtain panels before, but these are a special type that are built to deal with the conceptual environment in Revit. There's a lot of different patterns we can pick. Typically this will be located in your Autodesk library. So they're not a template, they're actually a family. And we're going to start with the rectangle surface pattern in this case. So basically a quad. To begin with, whenever I start a panel, I'll typically remove the fill in the middle. So what this environment is showing us is 4 points and 4 lines or reference lines. So each of these points is actually what we call an adaptive point. So it represents a sequential number of points that will define the positioning of this family. So you'll see we've got 1, 2, 3, and 4. And they represent a clockwise motion around the outside of the panel to point the normal or the outward facing panel away from the facade or up the page at the moment, the way we're looking at it. So we're going to start by adding some pivot lines in this direction along the panel, and then also some sub-pivot lines to enable the panel to fold inwards like this on both the top and the bottom side of the family. So we're going to use a tool in here which is the point element. You wouldn't have seen this tool in the family environment before. It's unique to the conceptual environment and quite useful at that. So we're going to add a couple of points. So we can place points on lines. You'll see this crosshair appear when you're doing that. So we're going to place 2 points here and 2 points here. And we'll just set these in a parameter that's called the normalized curve parameter. And basically this is how far along the line the point will be placed. So we're going to say 0.4. So 2 of them are going to say are from the beginning. You'll notice one of them is this way, one of them is this way. The other 2 are from the end at 0.4. So that's mainly because lines all have a direction in the conceptual environment. These ones are very easy to figure out the direction of because we know that they go in a clockwise, anti-clockwise motion around the panel. So once we've got these, we're basically going to use the spline through points tool. And what this tool does is it creates a curtain panel line, but what we're going to do is turn that into a reference line so that we can source that for multiple pieces of geometry. You can source geometry using lines, but they get used up and become a part of the mass's definition once you use them to generate forms. So we want to use that multiple times potentially. Likewise, we'll generate another line as well. And there are 2 reference lines. We then want to make the bisecting line where the apex and the fold occurs on the panel. So we will create 2 points here. Got another friend today. Coming to help out. Hopefully he stays. Or he's not going to do it, is he? Need you to move, man. I'm busy. Cats, gotta love them. Alright, so we're going to take these 2 and we're going to say beginning normalized curve parameter 0.2. One of them has moved all the way over here, so we want to grab this other one. And this one here. Sorry, that one there. We're going to normalize curve parameter them to 0.2 from the end. Actually, this one we need to associate to the beginning at point 2. Wait. Sorry, mate. I need to move back. Guys, cheeky. Got a little shoulder parrot. Alright. Sorry, it looks like my family was just freezing. So what we're going to do now is we're going to actually host some points on top of this point that we can offset away from there. So we're going to set work plane. And you can see I can tab through all the different work planes on this point. So typically points will always have work planes that are associated in all directions of reference lines on them. So you'll see here I have a reference plane away from this line, for example. So even though there's no plane here, there is once you add a line at that angle. So it's important to use these planes wherever possible. So we want to do the one facing up the page. I'm going to host a point there, and I'm going to ignore the warning. And essentially what I'm going to do with that is I'm going to offset that by 300. And I'm going to connect those 2 points with a line that I'm going to turn into a reference line. Now I don't need to do that, but visually I find that much easier to track what's happening, because as this point will move, we'll bring that point with it. And then from there we can also basically join the dots between all these until we're looking at basically a skeleton of the curtain panels. Likewise, we can do this again, set the work plane to this. Ignore the warning because we're about to offset the point. And then we'll move this up 300 and join these two together. We have a reference line. We'll join these, and you'll sort of see what I'm doing in a second once this all comes together. So I'll isolate category just to turn these all into reference lines at the same time. The shortcut for that's IC. And you'll see basically in principle I've got one folding component of the facade. So as this moves, you can essentially imagine the panel folding. So this is essentially what I would usually call like a rig in gaming that can move this all. I'm going to skip ahead one step just to one that I've prepared earlier, just to save you having to watch me do all of that myself. Sorry, I think my session's a little bit slow today. There we go. Oh, very slow today. Bear with me. Okay, so we're going to do a quad panel framed. So the point that I've reached at here is more or less that the panel is set up, but it has no parameters to guide it. So what we're going to do is start adding some parameters. So to these, we're going to add a parameter to the normalized curve parameter offset, because these will fold at the same ratio to each other, away from each other. And we'll just call this, we'll call this half fold. Actually, we'll call this fold parameter. We will jump ahead to another version again, which will probably have different names for these parameters, so don't get too used to the names of these ones. Likewise, we'll do the same for the mid parameter. And we'll take that one, and we will call that half fold. And we're making these instance based because we want every panel to be individually adjustable. And then beyond that, we'll take all these points and give their offset a parameter. Under here, fold offset. Okay, so we've given nearly everything we need to the panel parameter wise for the skeleton. But one thing we do need is we need a way to tell this apex how high it should be as the panel folds. So geometrically, you can imagine the panel folding. The panels aren't getting any smaller or bigger, they're just folding away. So essentially this should always be high enough such that this is half of the panel. So we're going to set up a reporting dimension in here. So I've basically done a dimension from this point to this point, which represents an edge of the panel. we're going to associate a parameter to it, and we'll end up calling this report length. So as this panel changes size in the model, this parameter will be updated by the family definition. So reporting parameters are special parameters that can only be used if they're hosted to something that is the core function of what size is the family. So in this case, these points are inherent to the family, and they're basically how the family is set out, and so we can make a reporting parameter associated to them. So now I'm going to go to my type parameters. And basically in here, if I just scroll along so you can see everything. Sorry, it's very slow. There we go. Okay, so by default, each panel comes with a solid type and a glaze type. I've got rid of the glaze type already. So we're going to take this fold parameter, and this is basically a number between 0 and 0.5 to represent how open or how closed the panel is going to be. So we're going to make half fold always equal to half of that. And the next thing we're going to need to do is set up the apex to a formula. So in principle, that formula is going to use these folding parameters to understand my apex is at 300 when I'm opening my panel, because I have two panels folded together in principle. So we can now say fold parameter is 0.2, and you'll see that apex is basically figuring out how high this needs to be. And in principle, the formula makes sense. You're welcome to have a think about how the formula works, but it's really just figuring out what size these are based on the ratio of how open this is on a factor of 0.5. So we'll move on from there. So the next thing we need to do is we need to create geometry to drive this element. So what we can do is we can use the create form tool. So this environment works quite differently to the family environment. You'll notice there's no extrusion, sweep, loft, swept blend tools in here. Instead, we have this button called Create Form. Now, Create Form is a context-sensitive tool. Depending on what you select, it will make different things. In this case, we're going to make a surface. So we've selected 4 sides. If I click on Solid Form, it'll prompt me for 2 options. One is 3D, and one is just a surface. We want to have thickness to our panels. So we're going to commit this one here. And we get the chance to say what's our positive and negative offset. So how far away from the surface and how far into the surface are we? And we're going to be 50 millimeters away. And we can connect this to a parameter called thickness straight away, because we'll use this to drive the rest of our family as well. And in principle, we can do the same for all the other pieces of the family. Again, we pick this. Thickness. So we do the same on the other side. In this case, I'll just skip one step to save some time. I'm also going to add a frame to the family. So for this, I'm going to have to do a sweep, and sweeps are a little bit different as well. So I'm going to draw on this work plane here, my profile, in which case I want to do a 150 millimeter frame. So I'm going to go 150 down. Every panel that meets another panel will form a double frame. So we're going to do a 500 million width here. So I want 30, 35, I'll do 30 millimeter mullion. It's a bit narrow, but it's okay. And we'll go up. So essentially we've just drawn 4 model lines. So what we're going to need to do now is select those 4 model lines. And then we need to select a path. So we're going to select these 4 reference planes. Oops, you can use Shift to unselect things. Cool. And again, Create Form is context sensitive. It understands what we want to do. So it's actually created a path that will move with the panel as well. You can also derive mass from mass. So I can take this edge and these other edges, similarly, a little bit finicky. And we can create a pane of glass from these 4 edges. And we'll give it thickness. In this case, we can actually inset it by setting the positive offset to -50 and the negative offset to 60 to end up with basically a cumulative 10 mil thickness in relation to this face. So in principle, we've set up the framework for a panel which will respond to the movement of these points. So I won't move these 4 here because I'm just going to jump to the next iteration of the family. So this is ultimately where you will end up with the family in the end. So you can see it's ready to go. So a few other things I've done. I've associated materials to all these elements using material parameters. This works like any other family where you set materials to elements. I've also added, I've kept the formula. I've kept the thickness parameter here. We'll just make that 50 while we're here. You can see I've got the half factor and the open factor. One thing I might do before I finish this part is I might turn open factor into an overridden parameter. And this is because I don't want the panel to ever be set to exactly 0, and I don't want it to be set to exactly 0.5, because this can potentially break the family in certain scenarios. I think in this case it can be 0.5, so I might leave that there, but I'm going to override it so it can never be more than 0.5. So I'm going to actually turn open factor into open factor overridden, which means we're not going to control this parameter. You can see all the other references to that update when I do that, so you don't have to worry about losing those references. And I'm just going to add another parameter called open factor. So currently this parameter is doing nothing. It's not connected to anything. But what we're going to do is build a formula that will basically drive itself based on what this parameter is. So we're going to use a formula with if statements. So I'm going to say if open factor is less than 0.01, it's 0.01. Otherwise, if open factor is greater than 0.5, it's 0.5. Otherwise, let it be open factor. And I'll close my formula. So in principle, this will override. So if my open factor is 0, you can say this reverts to 0.01. Likewise, if I go to 0.6, the formula will lock it to 0.5. However, if I'm between those two values, the formula will get to the end and let it be 0.35. So that's just the safeguarding parameter. I put these into families that usually are quite flexible, where a user might not quite understand the limitations of the family. I've also associated parameters to the panel, which is a white shade, the glass is a clear glazing, and the frame is an aluminium anodized. And in principle, that's pretty much all I have to do. So I'll just do a quick purge. Always good to purge before you finish a family. I'll save. So now I'm going to go into conceptual massing environment. But before I do, I'll just sort of show you the geometric condition that I'm trying to operate under in my model. So bear with me. So this is the final conceptual mass that we're aiming for. I will delete that. Okay, I'm just going to turn off my section box. So in this case, we've got a scenario where we're trying to clad a zone here to do a solar study. It's on a curve, just because I thought I might do something a little bit more complicated than a rectangle. And each floor is spaced by 4 meters. So we have 1, 2, 3, 4 floors. So we're going to replicate this in a conceptual massing environment. We have an elliptical floor plate here to generate our curve. So we have one side at 15 meters and the other at 32. So we are going to go into our conceptual mass. I'm just going to go to a non-perspective view. Okay, so this was basically made by going new conceptual mass. And there'll be a template that this will path to ultimately. So metric mass is usually what it would be. And this is located in the conceptual mass folder of family templates. We'll just go to floor plan to begin with. So in floor plan, it looks like a normal family. Obviously in 3D, you can see it looked quite different. What we're going to do here is we're going to use some model lines to draw our condition that we want to start with. So that's a 32 meter in this direction and a 15 meter in this direction. And we're going to draw a partial ellipse. This is a half ellipse, so we need to be careful. I'll just make sure I've drawn that correctly. Yes, I have. So we need to be careful that we get the right distance of ellipse here. So we actually need to do 64 and then trim. You'll notice that I've drawn this direction, then around. I'll draw another one the other way, just so later on you can see why draw direction is important. So I've drawn that one in the other direction. You'll remember when I was saying before that it's important to understand that lines have directions in conceptual environments. So the same goes for lines that you draw as well as reference lines. So I'm just going to trim this one up. So in principle, what I have, I'll just turn on my annotation categories so we can see everything and unlock the view. So we have two model lines and we have a level. So in this environment, we're going to create some new levels. It doesn't matter what they're called, but basically we're just replicating the setup of our model. So we need 4 of these, because we're going to use these as references to drive our elements. So what I'm going to do now is I'm just going to copy these to the top level. So you'll see I've got these here. And I'm going to use the last geometric condition. So I'm going to turn these into reference lines just so we can source them. And we're going to do a loft. So lofts will work between profiles, but also lines. So if I create form on 2 elements, it creates a loft. And that enables us to have a surface. There you go. So what we have now is surfaces. I'm going to operate them both at once. So there's a tool up here called Divide Surface. As soon as we click this, you'll see our surface changes how it's set up. Currently it has no pattern applied to it. But as soon as we select this, you'll see that we're dealing with U-grids and V-grids. So U-grids are left to right, V-grids are top to bottom. So essentially we want to take away our U-grid and use these levels to define our U-grids. So we're going to do what's called an intersect list to achieve that. I'll just take the U-grid off this one as well. And under its properties, you can actually set the layout. But first, we're going to go to this rectangle pattern because we're using a rectangle panel. Okay, so we're just going to say, maybe we'll say 15 for our V-grid. And our U-grid's dictated by this. Actually, that might be a little bit too intense. We'll just say 12. Okay. So on both of these surfaces, we're going to do an intersects list. I think I have to do these one at a time. So there's an option here called intersects list. We're going to turn off the pattern and turn on the surface, just so it's easy to visualize what we're doing. So you have a lot of controls over how you can represent these surfaces. So I'm just going to do one of them first. If I go to intersects list, I can actually set up lines that will bisect these with U-grids. There you go. So you can see that now it's actually being driven by the levels instead. And the reason why I'd want to do this is that if one of these levels changes, the grid changes with it. So that's quite powerful. I'm also going to just do intersects list for the tops and the bottom. I'll double check. I may not need to do that actually. We'll see what happens if I don't. Okay. So from here, I can load in my panel. And I will just reopen and then load into project and close to do that. You could load from library in this case. I'm just going to load into this mass. Okay, so what I can do now, there's 2 ways to apply adaptive components. One of them won't work for this tutorial. If all your components are exactly the same, you can place the adaptive component and use what's called a repeater. So at the moment I can't see any nodes on my surface. So if I go to this little box here, I can turn on nodes, and now I have nodes available at all my intersections, which is quite good, because now I can host elements to those nodes. So I can go 1, 2, 3, 4, and it's built that panel. So you'll see here that the reason why it can be important to draw your arcs in the right direction is if I do the same on this surface, 1, 2, 3. It's being friendly in this case. However, we'll see that something might not work after that. But I can use what's called a repeater, which is this button here. And this will just repeat that across the whole facade. Now, the only reason I don't want to use this tool, it looks great, but the problem is if I change one of these, they all change. Everything becomes a copy. It's like an array in principle. And this is where you can see that kinetic nature of the facade taking effect. So that's pretty cool. It's fun to see it all change at once. But ultimately, we want to drive these more intelligently in the end. So what we really want to do is take off this repeater. You can go remove repeater as well. But instead on the rectangle, we want to set this to ABG quad panel. And this will now apply that panel on a pattern basis. Here we go. So this is why draw direction is very important. You'll see that it's actually drawn it back to front, and that is because the line direction didn't support the orientation of panel that we needed in this case. So we actually needed to draw it the other way around. So we'll do this one instead. So remember, we drew this one in the other direction, and you'll see these ones actually face out like we want. So that's ideally what we need to do. So it's always important to make sure you're drawing in the right direction. It's good to experiment and check this as you go, just to make absolutely sure that this works. Okay, so that's pretty much our frame set up. If I take one of these panels, you'll see that I have the ability to manipulate it still. But if I manipulate this one, it's manipulated on its own, which is good. So these aren't connected anymore. So if I go select all, visible in view, actually sorry, in project, I can make these all, say, 0.3. just for this scenario, but the next tutorial will deal with how to manipulate these on an instance basis. So we'll just load this into our project now. Okay, if I go to ground floor, component, place a component, place on work plane, and I'll pick mass done, which is basically a copy of the one that I worked on earlier. And I'll click. It's going to place that mass as a family instance in this case. So if we want to manipulate any of those panels individually, we need to do it within the family itself. But luckily Dynamo can work in this environment as well, which we'll see in the next session. As you can see, they do take a while to place. So it's good to minimize how many of these you use to just the number that you need, because they can be quite complicated otherwise. I'm just going to move this here. And there we go, that's it justified. Not quite, but almost. I wasn't quite accurate enough with this example. But if you were more careful than me, then there you go. So this is pretty much what you end up with. So in the case of this family, I actually adjusted them by row. So you've got the top row, 0.1, 0.2, 0.3, and 0.4. So this is where you can see that kinetic action on the facade occurring. If I tab select one of these, you'll see I can't manipulate that. I need to do that at the project level. But that's pretty much how you'd achieve a kinetic facade. There's actually ways to control these panels in Dynamo without using a divided surface as well, using a package called Lunchbox. I'll probably cover that in my next session briefly, because I find Lunchbox can be easier to work with than divided surfaces, and also a lot faster too. But in principle, that's pretty much the tutorial. So I'll just go back to the presentation. So the next session we're going to be running through is how to map an image onto that facade for a driver as the solar heat behavior, so that the panels can basically respond to a solar heat. So thanks for listening today. We're going back to, I guess, the main series, where this is our final stage, using a conceptual mass. You can see here an example of another panel I set up, which I think is another building in the world where it's actually a triangulated panel that folds inwards in 3 directions. It was a little bit complicated for this session, so I didn't make it for that reason in this tutorial. But thanks for listening today, and I look forward to having you along to the next session. If there's any topics you want to request in the meantime, feel free to leave a comment, or if you have any feedback on the workflow, feel free to follow and subscribe if you're enjoying what you see. I'll be trying to upload a video per day, and thanks for listening. Take care. Bye.